So, your data science skills got you in the door. But to build machine learning systems that actually last, you got to start thinking like an engineer. And that's exactly what this explainer is all about. We're going to bridge that gap, taking you from the comfort of your exploratory notebooks to the world of production-ready MLOps. And we're starting with the absolute foundation, your data.
So here's what we're going to cover. First, we'll talk about that big mindset shift from science to engineering. Then, we'll dive into choosing data formats, loading data when it gets huge, splitting it up for production, and wrap up with the super important question of shuffling.
All right, let's kick things off with something you probably think you know like the back of your hand, the dataset. But we're going to look at it through a new production-focused lens.
Right? You obviously know what a dataset is. It's the lifeblood of every model you build. But in MLOps, the definition isn't what matters. It's the engineering discipline we bring to it from the very beginning. How we handle our data from day one, that's what separates a project that works from one that's just a painful mess. You know, in a notebook, you run a quick .shape or .d types. It's a gut check, right? It gives you a feel for the data. But in production, that gut check needs to become a set of deliberate, automated engineering choices. That's the pivot. And it starts with our file formats. Okay, this is our first major level up moment. It's time to move beyond just reflexively typing read CSV and to start thinking strategically about the right file format for the job. This is a classic science to engineering pivot right here.
And believe me, this isn't some academic exercise. The format you pick has a real, measurable impact on your cloud bill, your data access speeds, and the efficiency of your entire pipeline. If you get this wrong, you're basically building your house on a slow, expensive, and shaky foundation.
What's so interesting here is the core trade-off. See, row-based formats like CSV are fine when you need to grab an entire row at once. But for analytics, where you're usually just selecting a few columns out of maybe hundreds, a column-oriented format like Parquet is a total game changer because it only reads the specific columns you ask for. That makes your queries dramatically faster.
So, the rule of thumb is this: match the format to the job. Use something super efficient and columnar, like Parquet, for your data warehouse and your big analytical queries. Then, when it's time for model training, switch over to a highly optimized binary format that your specific framework, whether it's TensorFlow or PyTorch, can just gulp down at maximum speed.
Okay, let's keep building on this. You've stored your data efficiently, but what happens when it gets, well, huge? So huge that just loading it with pandas makes your laptop sound like it's about to achieve liftoff.
So how do we get out of this jam? You have to stop thinking in terms of slow, one-at-a-time Python loops. The real path to performance comes from these 4 patterns: vectorizing your operations, using all the CPU cores you have, being lazy and computing only when you absolutely have to, and, when all else fails, spreading the work across a whole bunch of machines.
All right, so if your data is big but not, we need a whole data center big, Polar should be the first tool you reach for. It's written in Rust, so it's incredibly fast. It's built from the ground up to use all your cores and to be lazy. It is basically pandas on rocket fuel.
And what if you're a SQL fan? Well, if you love writing SQL for analytics, but you want to do it at blazing speeds right inside your Python script, you need to meet DuckDB. Just think of it as a super-powered, analytics-focused SQLite that can run queries directly on your Parquet files. It's amazing.
And then, of course, there's the heavyweight champion. When your data truly gets too big for one machine, Spark is the undisputed king. It is the industry standard for taking a massive job and distributing it across an entire cluster of computers.
All right, we can store our data right, we can load it at scale. But look, all that speed and efficiency means nothing if we mess up the most critical part: preparing the data for training in a way that makes our model reliable and trustworthy. In supervised learning, this is step 0. It is non-negotiable. We have to explicitly tell the model, hey, look, here's all the information you can learn from. That's our X. And this is the thing I want you to learn how to predict. That's our Y.
And the code for this is so beautifully simple, right? It's a clean, unambiguous contract. This little snippet of code tells any ML algorithm, and just as importantly, any other developer on your team, exactly what the inputs are and what the output should be.
So why do we take this perfectly prepared data and then immediately hide a piece of it away? Well, this is probably the single most important step you can take to honestly evaluate your model and to avoid the cardinal sin of machine learning, overfitting.
You have to remember, the test set is not more data for training. It is the final exam. It is the only way you can get an honest, unbiased measurement of how your model is going to perform in the real world on data it has never, ever seen before.
This split is what builds trust.
Finally, let's zoom in on one tiny little parameter in that train-test-split function. It's something people often just set and forget, but it has absolutely mission-critical consequences for your model.
The decision to shuffle or not is non-negotiable, and it all depends on your data. From most datasets, like customer info, you must shuffle. It ensures your train and test sets are random, unbiased samples. But if you are working with time series data, like stock prices, shuffling it will destroy the very chronological pattern you're trying to learn. You'd literally be training on the future to predict the past, and your model would be completely useless.
And this quote from our source material just nails it. You have to ask yourself, does the order of my rows contain valuable information? If the answer is no, shuffle away. If the answer is yes, you absolutely must preserve that order.
Thinking critically about data formats, loading performance, splitting strategies, this is the leap from data science to MLOps. So the question you have to ask yourself is this: is your current data pipeline built for a one-off experiment in a notebook, or is it engineered to deliver real, reliable value in production? Making that shift is what will define your success as an ML engineer.